So in this video I'm going to talk about the question which appeared in IIT-JAM 2022 from thermal and statistical physics. Okay, so let's continue with the first question. The statement is: consider a classical ideal gas of n molecules in equilibrium at temperature T. Each molecule has two energy levels with energies minus E and E. The mean energy of the gas is, okay, so we can find the expression for the mean energy by making use of the partition function approach, and the energy levels which are accessible to the n gas molecules, they are having energy minus E and plus E. Okay, so we are having n gas molecules that is given to us. Okay, so let's try to find out the partition function for one single gas molecule first. So that is given by Z1 summation for I gi exponential minus beta ei. So here gi, that's the degeneracy factor, basically degeneracy. Okay, so here it is equal to unity. Okay, so therefore the partition function for one single gas molecule, it will be g1 exponential minus beta e1. So e1 is minus e, so that will be exponential, minus minus will become plus, exponential beta energy of the first level, okay, plus g2 exponential minus beta e2. So g2 is unity, exponential minus beta, and multiply by energy which is plus e, so minus this one. Okay, so this is the partition function for a single gas molecule. So now we will obtain the average energy for a single gas molecule, which is given by E, the average energy, and it's connected to the partition function via the relationship minus curly beta of logarithmic of the partition function, and this is equal to minus curly beta ln of exponential beta e plus exponential minus beta e. Okay, so after differentiation with respect to beta, it turns out to be equal to minus 1 upon exponential beta e plus exponential minus beta e, and then differential of exponential beta e plus exponential minus beta e with respect to beta, and this is equal to minus 1 upon exponential beta e plus exponential minus beta e, and then e exponential beta e plus minus e exponential minus beta e. So after rearranging all these terms, we obtain this is equal to minus e outside, and then exponential beta e plus exponential minus beta e divided by exponential, sorry, yeah, it will be a minus here because we are having minus outside, and here again another minus from here. Okay, so it will be minus, sorry, okay, exponential beta e plus exponential minus beta e, and this is nothing but, so we can write it here, e, that is equal to minus e, and then this is, if you just take a look at this, and this is equal to tan hyperbolic beta e minus e tan hyperbolic beta e. So that is the average energy per particle, because we are given a system of n molecules. Okay, so the average energy for n molecule, that will be simply the number of gas molecule times the average energy per molecule. Okay, and that is equal to minus Ne tan hyperbolic beta e. So this is our final answer. So here the correct option is, therefore it is C, because here beta, that is equal to 1 by kBT. Okay, let's continue with the next question. This is a very simple question, and it's based upon the definition of the isobaric expansivity and isothermal compressibility. Okay, the statement is, at certain temperature T, let beta and kappa denotes the volume expansivity and isothermal compressibility of a gas respectively. Then the ratio of the beta and K is equal to, so we have to figure it out. Then what is this quantity equal to? So here we will make use of the definition of the beta, which is the isobaric expansivity, and that is equal to fractional change in volume with T expansion its with respect to temperature. Okay, and under isobaric condition, that's the first definition we are going to use. And another quantity is its kappa. Okay, kappa T, basically kappa T, that's isothermal compressibility basically. Again, it's a fractional change in volume, 1 by V delta V, that's a fractional change. And now it's the isothermal compression. Compression is with respect to pressure, so that's why a pressure in the denominator and under the condition of constant temperature. But now, just to make this quantity positive, a negative sign is introduced here, and the reason is that when we increase the pressure, for instance, the volume, there will be a decrease in the volume. Okay, so therefore this differential will be negative, and negative multiplied by negative, that will give you ultimately a positive quantity. Okay, so that's why a sign is introduced here, negative sign is introduced here. Now let's try to understand what will the value of the ratio beta divided by kappa T. So just substitute these definitions here. 1 by B dV by dt at constant pressure divided by minus 1 by B dV by dP at constant temperature. And after rearranging, so this will cancel with this quantity, and this is equal to negative of, so I am taking this quantity in the numerator, so it will become dP by dV at constant temperature, and then dV by dt at constant pressure. Okay, so here we will make use of the reciprocity theorem. So that is beta by kappa T. I am going to write it as beta by kappa T, that is equal to dP by dt at constant volume. So here I have made use of the result which I am calling as reciprocity theorem. So which says that if we are having three variable, for instance dx by dy, by keeping third parameter constant, this can be written as with negative sign dx by dz by keeping y constant, and then dz by dy by keeping x constant. So when we made use of this result here, so we obtained beta by kappa T, that is equal to dP by dt at constant volume. So that means the correct option here, it is dP by dt at constant. Okay, this one, A. Okay, so therefore A is the correct option here. Now let's continue with the next question. So the statement is, an ideal gas in equilibrium at temperature T expands isothermally. Okay, so we are given a situation, we are given an ideal gas and it's undergoing isothermal expansion. So that means for an isothermal expansion dt, that is equal to 0. Okay, and because it's an ideal gas, so for the ideal gas, if dt is equal to 0, so then that is equivalent to say that du it's also 0, because the reason is that for an ideal gas the total internal energy is purely kinetic in nature, and if temperature doesn't change, then that is equivalent to say that du it's also going to be 0. Okay, so the statement is the ideal gas, it expands isothermally to twice its original volume. Okay, so that means another point that is given to us, V1 that is equal to V and V2 is equal to twice the initial volume. Okay, if delta S, delta U and delta F denote the changes in the entropy, internal energy and Helmholtz free energy respectively. So then we have to figure out that which one of the following four options they are going to be correct. Okay, so let's try to figure it out. So first condition we have already determined. So let's try to understand what happens to the entropy when a gas undergoes isothermal expansion. Okay, so the definition of the entropy is ds, that is equal to dq by T. Okay, so that means if somehow we are able to evaluate this quantity dq, then we will be able to figure it out what is going to the corresponding entropy change when gas undergoes isothermal expansion. Okay, so here we will make use of the first law of thermodynamics, which says that du, that is equal to dq minus dw, because it's an isothermal expansion. So du, that's equal to 0, so that means dq, that's nothing but that is equal to dw, and which in turn is equal to p dv. So dq is equal to p dv. Okay, so by making use of this definition, we can evaluate the net entropy change delta S, which is equal to integral of ds from some initial state to final state, and that is further equal to dq by T from some initial equilibrium state to final equilibrium state. Okay, and this is further equal to substitute the value of dq from here, that is p by t dv, and because the volume is changing, so we can write it here v1 to v2. And if further making use of the ideal gas equation, that is pv, that is equal to nRT. So here p turns out to be equal to p, that is equal to nRT by b. So here the corresponding entropy change will be n r t upon t and then dv by v from initial volume v1 to v2. So therefore the corresponding entropy change in this situation delta S, that is equal to n r ln v2 upon v1, and that is equal to n r ln 2, and this is greater than 0. Okay, so because v2 it's twice the initial volume, so if you substitute the value of v2, that is equal to 2v, and divided by v, that will give you n r ln 2. So therefore the corresponding entropy change for this case, it's greater than 0. So that's the second point that we have observed. Okay, now let's evaluate what is the corresponding change in the Helmholtz free energy. So if you just recall what is the change in Helmholtz free energy, that is equal to, in terms of the thermodynamic variables, so this can be rewritten as minus s dt minus p times dv. Now because it's given that it's the isothermal process, so for isothermal process dt will be equal to 0, so this term will become 0. Now df, that is equal to minus p dv, because it's given that it's an expansion, so for an expansion dv, that is equal to b2 minus b1, and that is greater than 0. So therefore df will turn out to be equal to minus p dv, which is definitely less than 0. Okay, so we have figured out all these three conditions. So the final conclusion is that for the given statement, for the isothermal expansion of the ideal gas, the first thing is that delta U, that is equal to 0, and delta S, that is greater than 0, and delta F, as we have figured it out, it is less than 0. So let's say which condition satisfy all these three conditions, that is delta S is greater than 0, delta U is equal to 0, and delta F less than 0. So therefore V option is correct here. Let's continue with the next question. So the statement is, in a dilute gas, the number of molecules with free path length greater than x is given by this expression. So we are given this expression. So basically this is the survival equation, okay, where n naught is the number of molecules and lambda is the mean free path. The question is the fraction of molecules with free path lengths in the range between lambda and 2 lambda is, okay. So because the hint, it's already given the statement of the question, so let's try to figure out which one is the correct option here. Okay, so the fraction of molecule fraction of molecules which survive the collision up to a distance of x. Okay, so that is given by, that's a fraction basically, and it's given here in the as a hint. Okay, that's exponential minus x by lambda basically. Okay, now so we have to figure out, we have to find out that fraction of molecules which have the path length between lambda and 2 lambda. So that fraction we have to find. Okay, therefore the fraction of molecules with path length between lambda and 2 lambda. Okay, so definitely the molecule which will survive a path length of lambda, that will be larger than the molecule which will survive a path length of 2 lambda, because after traveling a distance of lambda, again they have to again further travel a distance of lambda. So in this distance again some of the molecule they will collide and corresponding number will reduce. Okay, so and this quantity will be equal to exponential minus lambda by lambda, which is the fraction of molecule which have survived a distance of lambda. Okay, minus exponential minus 2 lambda by lambda. So here what we have done is we have replaced x with lambda and 2 lambda respectively. Okay, and this is nothing but this is equal to e power minus 1 minus e power minus 2, and after solving we obtain this is equal to 1 by e minus 1 by e power 2, and that is equal to e minus 1 upon e power 2. Okay, so e minus 1 upon e power 2. So therefore D is the correct option here. So let's continue with the next question. The statement is, for a certain thermodynamic system, the internal energy U, that is equal to PV, and P is proportional to T square. Okay, the entropy of the system is proportional to. So we have to determine the correct option out of the given 4 option. So let's write the given conditions. So we are given that U, that is equal to PV. Okay, and we are also given that pressure, it is proportional to T square, or we can write it as P, that is equal to some constant K multiplied by T square. Okay, so now this implies, the first condition implies that pressure, that is equal to U, the internal energy divided by volume. Okay, so and by making use of this definition here, from the second condition here, temperature, that is equal to P divided by K, its under root. Okay, so we will make substitution of P from here into this equation, so it will become equal to U by B, U pressure, that is equal to U by V, U by K, and then V and its power 1 by 2. Okay, now by making use of the relation 1 by T, that is equal to ds by dE, or ds by du, you can say. Okay, so this equation basically we got it from the first law, which says that du, that is equal to TdS minus PdV. Okay, so from here if you just take a look at this equation, so T, that is equal to du by ds by keeping volume constant, and when you invert this equation, so 1 by T, that is equal to ds by du at constant volume, so like this. Okay, so because T it's available with us, so 1 by T will be reciprocal of this, which is equal to K B upon U and its power 1 by 2. So okay, so we made use of this result. So from this relationship, let's call this as equation 2, and let's call these results as equation 1. So equation 2 implies that ds is equal to, okay, so ds will be equal to K V power 1 by 2, and then U from the denominator with power minus 1 by 2, and then du. Okay, so when you integrate this equation, so then we obtain delta S, and delta S you can write S final minus S initial. So, okay, so from this equation we obtain this result. Okay, so because it's with respect to u, so this can be written as k b power 1 by 2, and then its integral will be u power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. Okay, and then after solving this is equal to, so here we will have a factor of 1 by 2 from the denominator, so that will become 2 in the numerator. Okay, 2 times kb power 1 by 2, and then u power 1 minus 1 by 2, that will give you 1 by 2. Okay, so we can rewrite this equation as SF minus Si, that is equal to 2k power 1 by 2. So I'm writing that as k dash. Okay, k dash, and then v power 1 by 2 into u power 1 by 2. So I'm writing it v u power 1 by 2, or SF, that is equal to k dash ub power 1 by 2 plus Si. So note that here k dash I have rewritten this to be equal to 2k power 1 by 2. Okay, so therefore from here we conclude that the final entropy is proportional to ub power 1 by 2. So therefore D is the correct option here in this question. Let's continue with the next question. The statement is the figure shows a section of the phase boundary separating the vapor and liquid states. Okay, so here below this line A, B, C, we are having the vapor phase. Okay, and then of water in PT plane. Okay, here C is the critical point. So this is the critical point, and mu1, V1 and S1 are the chemical potential, specific volume and specific entropy of the vapor phase respectively. So here in the vapor phase the parameters are, let me draw the diagram, and then okay, it's a PT diagram, which is also known as the phase diagram basically. Okay, so here we are given a situation something like this. Okay, here we are having point A and point B, and then the critical point C is the critical point basically. So here it's the vapor phase here. Okay, and note that it's just below the critical point. Okay, so beyond the critical point it's something else. Okay, so that I'm going to discuss here. Okay, so this is the vapor phase, and this is the liquid phase. Above this line it's the liquid phase, and it's given that in the vapor phase the corresponding parameters are mu1 and then V1 and S1. We have mu1, that's a chemical potential, and V1 that's the specific volume, and S1 that's a specific entropy of the vapor phase. And correspondingly here we are having parameter mu2, sorry, it's B2, not mu2, B2, and then S2 here. Okay, now then okay, so we have to figure out the correct option out of these given 4 options. So now if you just recall what you have learned in the thermodynamics, so along the this common line that exists between 2 different phases. Okay, so along that line, so I mean from A to B, along the line AB. Okay, so the condition that should be valid is mu1, that should be equal to mu2. Okay, because this is the line where both of these 2 phases coexist. Okay, and if you just move along this line from one phase into the another phase, the chemical potential that will change basically. Okay, but along the line which separates just the 2 phases, the chemical potential that's bound to be identical. And for instance, for the when we are at this point, let's say, okay, so here for any point, let's say let me call this as point D. Okay, this one I'm talking about. So at point D, we will have the situation mu1 that will be smaller than mu2. Okay, because the phase which is more stable, that will have a lower chemical potential. Similarly, if you consider another point here, somewhere here in the liquid phase, and let's call that at point E. So at point E, the relationship between the chemical potentials will be mu2 that will be smaller than mu1. Okay, so therefore what we conclude is that along line AB the chemical potential that's identical. Okay, even from B to C again this condition will be valid. Okay, the chemical potential is bound to be similar. Okay, now what are the other options? So S1 equal to S2 along AB, and V1 equal to V2 along AB, no, and B1 equal to V2 at point C, yes. This is the specific volume. So let's talk about the critical point here. So when we use the word critical point, so it means, so at critical point, at point C, which is the critical point, the distinction between the liquid phase, liquid and vapor phase disappear. Yes. So that means both it's not possible to distinguish between these two phases at critical point C and above critical point C. Okay, so it's like a dense gas. The liquid, it appears like a dense gas. So that means it's merely a gas phase basically. Okay, so at this point the B1, the specific volume, will be identical in this case. So therefore the correct options here, B1 that is equal to V2 at critical point C and mu1 equal to mu2 along point A. So therefore A and D, these are the correct options here. A and D are correct here. So let's continue with the next question. The statement is, for an ideal gas, AB and CD are two isothermals at temperature T1 and T2. Okay, so here these two processes AB and CD, these are isothermal, okay, at two different temperature T1 and T2, such that T1 is larger than T2. Okay, so this is given to us, and further AD and BC represent two adiabatic paths as shown in the figure. Okay, so let BA, BV, BC and VD be the volumes of the gas at points A, B, C and D respectively, and it's further given that the ratio of the volume at point C and B, VC by BV, that is equal to 2, and we are asked to find out the ratio of the volumes at point D and at point A, that is equal to how much. Okay, so let's try to understand how we can do handle this problem. So as it's given in the statement that point B and C, they are connected by a adiabatic process. Okay, so that means process BC, it is an adiabatic process, adiabatic process. Okay, so note that point B, this is at temperature T1. Okay, so this is at temperature T1, and point C, this is at temperature T2. Okay, such that T1 is larger than T2. Now here the volume at point B, it is BV, and volume at point C, it is VC. Okay, so we will make use of the equation that connects the temperature and volume for an adiabatic process. So for point B, I can write T1 and the corresponding volume at point B, which is BV, okay, and its power gamma minus 1, TB power gamma minus 1, that is constant for the adiabatic process, and this should be equal to the temperature at point C, which is T2, and then the corresponding volume at point C, which is VC, okay, power gamma minus 1. So here we are making use of the results that for an adiabatic process, TB power gamma minus 1, this is equal to constant. Okay, and from this relation we obtain the ratio between two temperature T1 and T2, that is equal to VC upon BV power gamma minus 1. Let's call this as equation 1 here. Okay, now same way process AD, okay, process AD is adiabatic, again it's adiabatic process. So that means again this relationship, it's again going to valid between these at points A and D. Okay, so let's write the corresponding equation for point A and D, because A is at temperature T1 with volume BA and D is at temperature T2 with volume VD. So for this case we can write for point A, I can write T1, the corresponding temperature at point A, which is T1, and the corresponding volume at point A, it's BA, T1 BA power gamma minus 1, and then the corresponding equation for point D, T2 VD power gamma minus 1. So this will give you T1 by T2, that is equal to VD upon VA power gamma minus 1. Let's call this as equation 2. Now if you just compare equation 1 and 2, so from equation 1 and 2 we obtain that VC 1 and 2 implies that 1 and 2 implies VC upon BB is equal to BD upon BA, and which is equal to 2. Okay, because BC by BB, that is equal to 2, it's given to us. Okay, so therefore here the correct answer is 2 here. Now let's continue with the next question. So we are given a situation where a box contains a mixture of two different ideal monatomic gases which are labeled as 1 and 2. Okay, in equilibrium at temperature T. Both gases are present in equal proportion. The atomic mass for the gas 1 is m, while the same for the gas 2 is 2m. Okay, if the RMS speed of gas molecule selected at random is Vrms, that is equal to x under root kT by m, then the value of x is. Okay, so let's try to understand this problem. So we are given two different same kind of gases, monatomic gases, but different masses. Okay, so we know that the root means the speed for the gas, that is Vrms. This is equal to, so I'm writing the expression for the gas 1. Okay, so that is equal to 3 kT upon m. Okay, this is for gas 1. Okay, let's call this a RMS 1. Okay, the k is the Boltzmann constant. Okay, so similarly we can write the corresponding expression for gas 2 Vrms 2, and that will be equal to 3 kT upon corresponding mass, that is twice the m. Okay, now so with these two expressions I can write the expression for the average speed for any molecule which is randomly selected, that is equal to V RMS 1 plus V RMS 2 divided by 2. So now make use of the expression 1 and 2, and this will be equal to, so when we substitute, so we will take the common terms outside. So from the first this equation we will have under root 3 here, and kT by m, that's going to be common in both of these two expressions. So under root 3 plus under root 3 by 2, and then divided by 2, and then multiply this by kVt by m, which is common in these two cases. Okay, and when we further solve this expression, so this turns out to be equal to under root 6 plus under root 3 divided by 2 under root 2, and then multiply by kVt upon m. Okay, and if you further solve this numeral value, so this turns out to be equal to, so V average after solving, V average comes out to be equal to 1.48 multiplied by kT by m. So therefore x is equal to 1.48. So that's our answer. So x is 1.48. Now let's take a look at the final question. So the statement is, a hot body with constant heat capacity of 800 joule per Kelvin at temperature 925 Kelvin is dropped gently into a vessel containing 1 kg of water at temperature 300 Kelvin, and the combined system is allowed to reach the equilibrium. The change in the total entropy delta S is joule per Kelvin. So we have to find the delta, what is the delta S for this entire system. Okay, so let's try to figure out what are the given parameters, and then try to find out the total change in entropy. Okay, so here we are given for the system 1 C1, that's the principal heat capacity, that is 800 joule per Kelvin. Note that it's a principal heat capacity, not the specific heat, and the corresponding temperature for the object is T1, that is given to be 925 Kelvin, and for the water, the mass of the water, that is 1 kg, okay, and the corresponding temperature for water is T2, let's say that is 300 Kelvin, it's given, and corresponding specific heat, note that it's a specific heat, not the principal heat capacity, 4200 joule per kg per Kelvin. Okay, so let's assume that when these two systems they are combined, then the final temperature is, let's say, let TF be the final temperature. Okay, so then by applying the principle of calorimetry, which says that heat lost by one system, heat lost, that is equal to heat gained by the another system without any loss to the surrounding. Okay, so then here, because initially the block it was at higher temperature, so heat will be lost by this object, so the corresponding heat lost will be C1 delta T. So with 925 is the initial temperature, and let's say as I said, TF is the final temperature, so C times delta T, so that will be equal to the heat lost by the object, and this is equal to the heat gained by the water, which is MW, and then CW. So here we need to multiply by the mass, because we are given the specific heat, which is per kg. Okay, so that's why we are multiplying with the mass of the water. Okay, and then the corresponding temperature change, which is TF minus T initial, because here for the water the temperature has raised to a final value of TF, so that's why TF minus 300, the initial temperature. Okay, so after substituting a value of the constant, so C1 it's given to us as 800, and then 925 minus TF. So basically we want to determine TF from this condition, and MW, that's 1 kg, multiply by the CW, which is 4200, and then TF minus 300. So here these two zeros, they will cancel with each other, and after solving this equation, so we obtain 7400 minus 8 times TF, and that is equal to 42 TF minus 12600, and when we solve this equation, so we will obtain TF, that is equal to 400 Kelvin. Okay, so now we have obtained the value of the final temperature for the composite system. Now we have to evaluate the corresponding entropy change for the individual system, and then by adding those two quantities, that will give us the required value of delta S. Okay, so now let's evaluate the entropy change for the block. Okay, entropy change for block. Okay, because for the block the temperature is changing from initial value, which is given to 925, to a final value TF, which is 400 Kelvin. Okay, so the corresponding entropy change, let's say that is delta S1 for the block, and this is equal to C1 ln the final temperature divided by the initial temperature. Okay, and this is equal to C1, what is C1, that's 800, that's given, and ln final temperature, which is 400 Kelvin, divided by initial temperature, which is 925 Kelvin. So let's call this as our result 1. Now the entropy change for the water, entropy change for water, that is delta S2, and this is equal to MW CW ln, because for the water also temperature it's changing, so final temperature divided by initial temperature, which is T2. Okay, so here it was T1 basically. Okay, so after substituting the values, we obtained 1 into 4200 and logarithmic of the final temperature 400 divided by 300. Okay, so therefore now the net entropy change will be given by net entropy change for the composite system delta S, that is equal to delta S1 plus delta S2 here delta S1 and delta S2, they are given by equation 1 and equation 2 respectively. So after evaluating these logarithmic quantities, because here in equation 1 it's ln 400 by 925, so this is going to be negative. So if we substitute these values here, we will obtain the final result. So delta S1 will turn out to be equal to, we just simply evaluate these quantities. So this will be 670 with a negative sign, 663352, and then plus value of the delta S2, which will come out to be equal to 1208 plus 2647, and after adding these two terms, we will obtain this result to be equal to 537.6 joule per Kelvin. So that's the corresponding entropy change for the composite system. So therefore our final result is this number.